Fibonacci sequence is one of the cornerstones of the math world. However, it's normally defined recursively, and this means if we want to find some Fibonacci number, we need to know all the Fibonacci numbers that came before it. Now, this can be quite cumbersome, so it would be useful and quite cool to work out an explicit formula for the Fibonacci numbers, and that's what we're going to do today. Okay, let me be more precise about how I'm defining the Fibonacci sequence. So I'm taking the 0th term to be 0, and I'm taking the first term to be 1. Okay, and then I'm defining the recurrence relation in the normal way. So to get the next term, you just add the two previous terms. Okay, so this is the standard way. Okay, you can't change this, but some people change what they define to be the first or the 0th term and what they define to be f1. Okay, and there's even some generalizations where they take those to be arbitrary constants, and those are quite cool, but we're not going to look at that today. And then what do we know about the Fibonacci sequence? Well, one cool fact is that as we go very far along the sequence, the ratios of the next term to the previous term, well, that approaches a very famous ratio, the golden one. Okay, and I've already made a video about the golden ratio, so go and check that out. But what do we know about the golden ratio? Okay, where does it come from? Well, one way to derive the golden ratio is from this quadratic. Okay, x squared is equal to x plus 1. Okay, it's a solution to this quadratic. In fact, there's two solutions. So one solution is x equals the golden ratio, which is 1 plus square root of 5 over 2. Okay, but I'm not going to write that because I need whiteboard space. And then the other one, which I just learned how to pronounce, is psi. Psi. Okay? And psi is 1 minus the square root of 5 over 2. Right? So we have two solutions to this quadratic. And what does it mean to be a solution? It means we can just plug it in and it will satisfy the quadratic, right? That makes sense. So we have phi squared is equal to, what's equal to 5 plus 1. Okay, but now I'm just going to rewrite this slightly differently. So instead of writing 1, I'm going to write 5 to the 0, and then I'm just going to explicitly write the power here. Okay, well this kind of looks Fibonacci-esque. We have a number, and then the previous number, and then the previous number. Okay, so 5 to some power, it looks kind of Fibonacci. Okay, so now let's just times the entire thing by, so I'm just going to write this in a different coloured pen, let's times the entire thing by phi to the n minus 2. Okay, and if I do that, I get, on the left hand side I get phi to the n is equal to phi to the n minus 1 plus phi to the n minus 2. And yes, now we've confirmed phi to some power does satisfy the Fibonacci relation, so that's quite cool, right? And then we can do the same thing with psi. Okay, so also we have psi to the n is equal to psi to the n minus 1 plus psi to the n minus 2. Okay. Well, now let's consider some combination of these two numbers, right? So let's take, I'll do this in black. Let's take un to equal a times phi to the n plus b times phi to the n, not phi, sorry, b times psi to the n, right? And now this should satisfy the recurrence relation as well, but let's go ahead and show that. Okay, so un is equal to, well, phi to the n is equal to, we said it was equal to phi to the n minus 1 plus phi to the n minus 2. And then here we have b times the same thing, but with psi now. Okay, so we have psi to the power of n minus 1 plus psi to the power of n minus 2. Okay? And now let's just collect the terms of the same powers. Okay, so this is equal to, well, it's equal to a times phi to the n minus 1 plus b times psi to the n minus 1. Okay, now let's collect the terms with anything with a power n minus 2. Let's do that now. So we have plus a times phi to the n minus 2, and then plus b times psi to the n minus 2. Okay, and this is equal to u to the n minus 1 plus u to the n minus 2, right? So this does satisfy the Fibonacci recurrence relation, okay? And the Fibonacci sequence, as I said up here, right, is explicitly defined by two things. Okay, we need the recurrence relation and two starting points. Okay, if we get two starting points and this recurrence relation, then that uniquely defines the Fibonacci sequence. Okay, so we already have one of those things. Okay, UN satisfies the recurrence relation. So now if I can force UN to satisfy the initial conditions, then this will be the Fibonacci sequence. Okay, this will be an explicit formula. So I'm after my goals are I want U0 to be equal to 0, and then I want, my second goal is for this thing to be satisfied. So I want U1, so that's supposed to be capital U, U1 to equal 1. Right, and if this can be satisfied, then I have my formula. So let's just plug that in, that's just simultaneous equations. So first goal, just plug in 0, I get U0 is equal to 0, which is equal to A plus B, right? So I get, rearranging that, this implies B equals minus A. And now, for our second goal, let's see what we get. So plug in 1, so we get 1 equals, plug in 1 in here, we get A times phi plus, well, B times psi. Let's change the B for minus A, okay, so we get 1 equals A times phi minus psi. Sorry, minus A times psi, right? Just plugging in B equals minus A. And then, well, we can collect terms, so we get 1 equals A times phi minus psi, okay? And then divide by this thing here, so we get A is equal to 1 over phi minus psi, which is in fact equal to 1 divided by the square root of 5. Okay, and I'm just going to triple check that in case I'm wrong. Yes, it is, nice. So, this is what we get, and you can check this just by using the definitions of phi. So now we have A, and what do we say B was? Well, B was just minus this, so we have minus 1 over square root of 5 for B, right? Now let's just plug that in to our formula for UN, so we get, I'll write this out here, we get UN is equal to A, which was square root of 5, okay, times phi to the n, minus, well, it's minus square root of 5, so that's already been absorbed onto the bottom, minus psi to the n, okay? And there we go, we have an explicit formula for the Fibonacci numbers, right? And yeah, that was an awesome derivation. That was super, super cool. I really enjoyed that one. Thanks for that video. If you enjoyed, like and give some comments. If you have any suggestions, that would be cool. I'm always in need of more video ideas. And yeah, thank you very much for watching. And from this video, I BINET'S formula, which will obviously be incredibly useful. Yeah, any questions?
So besides from this class, I mean, when are Fibonacci numbers ever going to come? When are we going to start to use them?
Well, to answer that question, I mean, I presume you have seen the spirals you can make with them online. It is
fantastic! We can see spirals. I mean, great. That's
what. Hey, you're so talking in my class. You get your PhD before you talk in my class. God damn it! I hate my job.
Hi guys, don't forget to subscribe to Maths.
Should I say, if I wanted to see pretty spirals, I would have taken a liberal arts.